Welcome once again to my YouTube channel, namely Knowledge Entertainment. And I'm going to start right from there where we have left in the previous video. First, we will discuss about the types of functions. Then, we'll find how to find a range of a function. We have learned in a previous video how to find domain. Today, we'll see how to find a range of a function. And then we'll move on to the composition of two functions and inverse of the function. So I'll start with the types of the functions. First one to be discussed is identity function. Identity function. The easiest one in the types of functions is identity function. A function f, or in general we denote identity function by I, a function I from R to R, the set of real numbers to the set of real numbers, defined as I of x is equal to x for every x belonging to the set of real numbers, is called an identity function, is called an identity function. Sometimes domain of the identity function is not R. Suppose I is identity function from a set X to the set X, or you can say any other set Y, defined as I of x is equal to x for every x belonging to the set X. And in such a case we write we replace I by the symbol IX or I capital X, which denotes that IX is the identity function with domain set as X. So it is the definition of identity function. And then the second one is the constant function, which we have discussed earlier. And after constant function is the polynomial function. Polynomial function. A function f from the set of real numbers to the set of real numbers, defined as f of x is equal to a naught plus a1x plus a2x square plus and so on, a n x raised to the power n, where n is a natural number and a naught, a1, a2 and so on, a n are real numbers, is called a polynomial function. Is called a polynomial function. So basically polynomial function means f of x is equal to some polynomial in x, maybe of degree 2, maybe of degree 3, maybe of degree 4. So in general we have written a polynomial of degree n, where n is the natural number. If n is 1, then this will be of the type fx is equal to a plus bx, and we will call it as a linear function. If n is 2, it will become fx is equal to a plus bx plus cx square, and we will call it as a quadratic function. If n is 3, it will become fx is equal to a plus bx plus cx square plus dx cube, and will be called as a cubic function, and so on. The next will be the biquadratic function, then quintic function, and so on. So it is the definition of polynomial function. The next one after polynomial function is rational function. So next we define rational function. A function f from the set of real numbers to the set of real numbers defined as f of x is equal to px upon qx, where qx is not 0. px qx are polynomials in x. This is called a rational function. That means a rational function is a function which is quotient of two different polynomial functions. So fx is equal to px upon qx means px is a polynomial function, qx is a polynomial function, and their quotient, and it is sure that denominator should not be 0, otherwise it will not be well defined. This function is called a rational function. And then we will move on to the next definition, and the next definition is absolute value function. Absolute value function, or you can also call modulus function. Modulus function. A function f from the set of real numbers to the set of real numbers defined as f of x is equal to mod x is called modulus function or absolute value function. Here, the graph of this function is very interesting because on the right side of the y-axis, this is your y-axis, this is your x-axis. On the right side of y-axis, what you will get x greater than or equal to 0. And if x is greater than or equal to 0, this mod x will become x. So it will become fx is equal to x. And fx denotes the y coordinate. So y is equal to x. And y is equal to x is the straight line passing through origin, making an angle of 45 degrees with the positive direction of x-axis. But when we move on to the left side of the y-axis, what will happen? X will become negative, and if x is negative, mod of x is equal to minus x. So it will become fx is equal to minus x. That means y is equal to minus x. And y is equal to minus x is the line, this line. This is also inclined to the x-axis at an angle of 45 degree with the negative direction of x-axis. So it is this line. This is the graph of fx is equal to mod x. This line as well as this line, this is the V-shaped graph of the function fx is equal to mod x. Then we move next on to the definition of signum function. Signum function is very much dependent upon the absolute value function. So let us define it as a function f from R to R defined as fx is equal to mod x upon x if x is not 0 and 0 if x is equal to 0. This function is called signum function. This is called signum function. One thing is to be noted here is that if x is not 0, that means x can be positive, x can be negative. If x is positive, this will become mod x is x, so x upon x is 1. And when x is negative, mod x will become minus x, so minus x upon x will become minus 1. So this function can also be defined as fx is equal to minus 1 if x is negative, 0 if x is 0, and 1 if x is greater than 0. So these lines, the graph of this function is also very interesting. What is the graph of this function? Let's have a look at. So again, suppose here is your y-axis, here is your x-axis, it is the origin. When your x is negative, that means we are talking about the left side of y-axis. The value of fx means y, the value of y is minus 1. So the value of y on the y-axis is minus 1. So this is the line. But we will not be exactly on the y-axis, so we are marking here a circle. That circle means this line is not touching the y-axis. It is just very close to y-axis, but it is not touching the y-axis. When x is equal to 0, your fx, that means y is also equal to 0. That means this is your origin. The coordinates are 0 and 0. Then when you move on to the right side of the y-axis, your x is greater than 0, fx, that means y is equal to 1, and y is equal to 1 is something like here. Again, it will not touch your y-axis, but it will go like this. This is the line. Here y is equal to 1, here y is equal to minus 1. Y means you can say fx. So your fx is 1 and your fx is minus 1, and when x is equal to 0, your fx, that means f of 0 has the value 0. So this is signum function. After signum function, there is one more very important function that is known as greatest integer function. Greatest integer function. So what is the greatest integer function? A function f from R to R defined as f of x is equal to box x. We read this as box x, or you can say greatest integer x. So fx is equal to box x, where box x denotes integral part of x is called greatest integer function. Is called greatest integer function. Now look at, every real number has two parts. One is integral part, the other one is the fractional part. For example, if I write 4.5, it is 4 plus 0.5. So 4 is its integral part, 0.5 is its fractional part. So the value of box 4.5 will be equal to 4, the integral part of the number 4.5. Similarly, if you write 0.007, this number, box of this, so again it has two parts. One is integral part, that is 0, and the other is fractional part, that is 0.007. So the value of box is the integral part, that is 0. When we move on to the negative numbers, suppose I write minus 2.37. Most of the people confuse that its integral part is minus 2. But you have to keep it in mind that fractional part is always positive, fractional part cannot be negative. So this number 2.37 with negative sign, if you break it into integral and fractional parts, the fractional part will become 0.63 plus, and the integral part will be minus 3. Because if you write it as minus 2 minus 0.37, here fractional part will be minus 0.37, and I have told you that fractional part is never negative, fractional part must be positive. So what we will have to do, we will have to add 1 here and we will have to subtract 1 here. This minus 1 minus 2 will become minus 3, and 1 minus 0.37 will become 0.63. So the integral part will be equal to minus 3. It will become equal to minus 3. So this is your integral part function. The graph of this function is also very interesting. Look at the graph of this function, how it looks like. So here is your y-axis, here is your x-axis. For your convenience, I am writing here 0, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. Similarly, I am marking the y-axis also. It is 1, 2, 3, 4, and it is minus 1, minus 2, minus 3, minus 4, and so on. When the value of your x lies between 0 and 1, including 0 and excluding 1, the integral part will become 0, and the value of the function will be here from 0 to 1, but not touching 1, because when it will be 1, the integral part will become 1. For every real number between 1 and 2, including 1 and excluding 2, the value of fx, that means the value of the coordinate y in the graph, will become equal to 1, because integral part of all the real numbers between 1 and 2 is 1. So the graph will be starting from 1, reaching 2, but not touching the line x is equal to 2. Similarly, between 2 to 3, it will be here. Between 3 and 4, it will be here. And similarly, you go to the left side of the y-axis, it will look like something like this, 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 and this. So these lines are looking like some steps. So why this greatest integer function is sometimes also known as step function. It is also known as step function because its graph looks like steps. So this is the definition of greatest integer function, and then we will move on to the next definition. And the next function is just like greatest integer function, it is the fractional part function. Fractional part function. A function f from the set of real numbers to the set of real numbers defined as f of x is equal to x minus greatest integer x for every x belonging to R is called fractional part function. And why? It's very easy, it's very simple to understand why it is called fractional part function, because as I have just discussed in the previous one, every real number has two parts. One is the integral part and other is the fractional part. So fx here, for every x, this x, if you break this x into two parts, its integral part, as we have denoted in the previous one, x has integral part as box x plus some fractional part, and fractional part we normally denoted by the curly brackets x and minus box x. So this is cancelled. What we are going to get is fx is equal to box x, and this is fractional part of the real number x. So fx is equal to fractional part of x is the fractional part function. Let us have a look on its graph too. So here is y-axis and x-axis, and I am marking here 0, 1, 2, 3, 4, 5, 6, and so on. On the y-axis I am marking only 2 points because I need only one. Just one will be required. When you start from 0 to 1, there will be only fractional part. because integral part will be 0. The number itself is equal to its fractional part. That means y is equal to x. That means fx is equal to x. And this will become a graph something like that. But just before reaching 1, what will happen? As we will reach the point 1, once again the fractional part will become 0. And it will go in the similar way up to reaching to the point 2. And once again it will become 0. And then again you will reach 1, 0, 1, 0 and so on. So this will be the graph of the fractional part function. Then there are some operations of the functions. That means addition of functions, subtractions of functions, multiplication of functions, multiplication by a scalar constant, and division, that means quotient of two functions. We will discuss these one by one. So first I am going to take addition of two functions. Addition of two functions. So addition of two functions is possible if and only if their domain is same. So I am defining, let f from some domain f to real numbers and g from some domain to real numbers. Domain, if not same, will work, but the problem will be that when you will add these two functions, the domain of the addition of the two functions will become the intersection of these two, the common portion. And that's why I was talking that the domain must be same, because if domain of the two functions is same, then domain of the sum of the functions is also the same one. But no problem if f has some different domain, g has some different domain, then what will happen to the domain of the function, that is the sum of these two functions, it will become the intersection of these two domains. So let f from df to r and g from dg to r be two functions, then f plus g from where to r? I have just told you that f plus g will have domain that is common to the domain of f and domain of g, that means the intersection of these two domains. So f plus g from df intersection dt, this will be the new domain of the sum of the two functions. Then f plus g from df intersection dg to r is defined as, definition is very simple, that f plus g of x is equal to f of x plus g of x for every x belonging to d of f intersection d of g. That means the image of x under f plus g is equal to the sum of images of x under the functions f and g. So this will be the definition of addition, that means sum of two functions. The subtraction is very much similar, so I'm just making amendments here. Subtraction of two functions. Let f from df to r and g from dg to r be two functions. Here again, the difference of two functions, that means subtraction f minus g, will have the domain df intersection dg, that means the intersection of the two domains of the functions f and g, that means their common portion. So if f and g are two functions, then f minus g, the difference of two functions, is again defined from df intersection dg to r and is defined as the same way f minus g of x is equal to fx minus gx for every x belonging to the common domain of two functions, that means df intersection dg. Then the product of two functions is again same, you can say similar. The only difference is that the symbol. So again amending here, I'm not going to write it again. So here I am going to change it as product of two functions. So again, once again, let f from df to r and g from dg to r be two functions. Then f into g. Once again, the domain of the product of the two functions is the intersection of the two domains. That means df intersection dg to r is defined as f into g. The product is equal to the product of their images for every x belonging to the intersection df intersection dg. So this is again same definition. Now we move on to the fourth one, that is quotient of two functions, which is a little bit different, not too much, but there will be a point where it differs from addition, subtraction and product, that means multiplication. So now it is quotient of two functions. Let f from df to r, g from dg to r be two functions, then their quotient function f upon g. Once again, the domain is a little bit changed. The domain is df intersection dg minus all those x where gx becomes 0. So that means now the intersection is there, but some points more are deleted, and these are those points where the denominator portion becomes 0 because it will create problem. Something upon 0 will not be defined. So now this is the domain. From this to r is defined as, and the definition is same. That means f upon f of g is equal to f of x divided by g of x. And it is a question, but now we have no problem because all those points where gx is going to be equal to 0 we have omitted. That means the denominator will not be 0 now, and fx upon gx will be well defined. So this is the definition of quotient of two functions. And now we move on to the very important definition of composition of two functions, and it is most important definition in this chapter of relations and functions because it will be used again and again when we will move ahead in limits and continuities and derivative and integration portion. So this definition is very much important to be clear in your mind. So how composition is made? There is a function f from some, I'm taking three sets. First of all, I'm taking three sets. One is A, other is B, the third is C. F is the function from A to B. This function I'm not writing here, I'm writing it here. F is a function from A to B, and G is a function from B to C. That means domain of G is the set B, and B is also the range of the set F. So that means what is the necessary condition is that domain of G is equal to range of F. That is the required condition for the composition of two functions to be defined. And we define it as, we write it like this, and we read it also like this: F composite G, not G composite F. It is F composite G because first we are to apply the function F here, and then we will apply the function G. some students I have seen, they read it as golf, or if written otherwise, then they read it as fog. So it is neither golf nor fog. It is simply F composition G. So what is F composition G of X? Is G of F of X. So first you apply the function F to the point X, you will get some result, and this result will definitely be in the range of the function. But since the range of the function is the same as the domain of G, so this Fx will be in the domain of G, and something which is in the domain of G, you can apply the function G on that. So you apply G on Fx and you will get the result in the set C. That means your Fx is here, it goes to its image Fx here, and it goes to its image G of Fx here, and G of Fx is same as F composite G of X. So this is basically the composition of two functions. That means one function is applied and then on the result the other function is applied. So we look at some example first. Suppose I am taking two functions. I am taking one function as, I am not going into the domain and into the range, I am simply defining fx is equal to 2x plus 3 upon 5x plus minus 1, and I am taking another function gx as 7x minus 2 over 3x plus 1. Now look at what is F composite G and what is G composite F. So first I am talking about F composite G of X. So it is G of Fx. You know G of X is 7x minus 2 upon 3x plus 1. G of Y will be 7y minus 2 upon 3y plus 1. G of P will be 7p minus 2 upon 3p plus 1. G of M will be 7m minus 2 upon 3m plus 1. In the same lines, G of Fx will be equal to 7fx minus 2 upon 3fx plus 1. And now substitute the value of fx at these two places. What you are going to get? 7 times fx. Your fx is 2x plus 3 over 5x minus 1 minus 2, 3, 2x plus 3 over 5x minus 1 plus 1. What is, if you solve it further, it will become 14x plus 21 minus 10x plus 2 over 6x plus 9 plus 5x minus 1, that is equal to further 4x plus 19 over 11x plus 8. Why I have calculated this, you will get to know soon. So this function f composite g of x is coming to be 4x plus 19 over 11x plus 8. This is your f composite g of x. This is your function f composite g. Now look at what is g composite f. Now we'll find g composite f of x. It is f of gx. Now f of x is 2x plus 3 upon 5x minus 1. So f of gx will be, as we have done earlier, 2 times gx plus 3 over 5 times gx minus 1. Now substitute the value of gx at these two places. 2 times 7x minus 2 over 3x plus 1 plus 3 over 5 times 7x minus 2 over 3x plus 1 minus 1 is equal to, on further solving, it will be 14x minus 4 plus 9x plus 3 upon 35x minus 10 minus 3x minus 1, that means 23x minus 1 upon 32x minus 11. Now look at what was your F composite Gx and what is your G composite Fx. They are not same. Even their domain is not same. The domain of this function is the set of all real numbers but not minus 8 upon 11. And the domain of G composite Fx is the set of all real numbers but 11 upon 32. That means these two functions are not equal. So in general, you can say G composite F is not equal to F composite G. It is in general. Sometimes they may be equal, but in general, G composite F and F composite G are not equal. Now, the next one is the definition of inverse of a function. In the previous video, I have discussed 1-1 functions, onto functions. 1-1 means injective function, onto means surjective function, and if a function is 1-1 as well as onto, then it is an invertible function, and if a function is invertible, then definitely its inverse must be there. So what is the inverse of a function? So let f from x to y be a function which is 1-1 as well as onto. Because if a function is 1-1 as well as onto, only then its inverse will exist. In such a case, a function g from y to x, now earlier it was x to y, since it is inverse, it must be from y to x. So a function g from y to x is said to be inverse of f if f composite g is equal to ix and g composite f is equal to iy. So in such a case, if these two conditions are satisfied, then we will say that the function g is inverse of f and vice versa. Here I have written f composite g as ix because the domain is the domain of f and domain of f is x, so it will be an identity function with domain x. Similarly, here the domain of g composite f will be the domain of g and domain of g is y, so it will be identity function with domain y. So it is the definition of inverse of a function. So I am stopping video here. In the next video, we will discuss how to find inverse of a function and what are the other methods related to inverse of a function. So once again, I would like to thank you for liking my videos, for sharing my videos and for subscribing my channel. Thank you once again.